Okay, hello and welcome everyone. In this video, I'm going to continue doing exercises from this set of problems. They're consumer theory problems, and so I'll show you the problems in advance in case you hadn't got them, and then I'll go through them. So here's the first one, question number 32. I don't know, you could pause the video and then take a screenshot and work the problems. That's question 32. We'll do question 33, that's this right here, question 34, 35, 36, 37, 38, 39, and 40. Okay, so that's the goal anyway. So hopefully I make it through. Hopefully I make it through. I'm making videos all day. We'll do it. All right, so Bob has $30 to spend, is willing to trade off good X and good Y at a constant rate. In particular, willing to trade B units of Y in order to obtain 4 units of X. Price of good X is 1, price of good Y is 2, so our price ratio is 1/2. Okay, I'm willing to give up B units of good Y for 4 units of good X. So my slope is going to be rise over run. Rise is minus B, run is 4, so my slope is going to be minus B over 4, but I'm just going to report this positive because I know this is a negative sign, that's a negative sign, it's going to cancel. So I'm going to compare B over 4 to 1/2. Suppose Bob optimally purchased 30 units of good X. Find the range of possible values for B and find Y star. Oh, well, what's beta got to be to consume only X, right? I have $30. X is at 1, so that means all X. I spent all my money on X, right? Price of X is 1. So the Alex solution happens if the MRS is bigger than the price ratio, so I need B to be bigger than 2 so that the MRS is bigger than 1/2. So that's what this is saying. Suppose Bob optimally purchased 15 units of good Y. Well, 30 divided by the price of good Y of 2 is 15. So if I exhaust all my money on good Y, this is an alley solution. This happens if the MRS is smaller than the price ratio. So I need for B to be smaller than, beta to be smaller than 2. And then X star is 0. And then suppose I purchase 10 units of good X, find the range of possible values for B. I mean, I'm going to buy some good Y, and so this is going to be a situation where beta is going to be equal to 2, exactly equal, so that the MRS is equal to the price ratio. That's what this is. And how much Y do I buy? I'm going to exhaust my budget. I'm going to need 10 units of Y. All right. Consider the quasi-linear utility function. So I have X to the 2/3 plus X2. Assume the prices are 2 and 3, so the price ratio is 2/3. Find the Marshallian demands when M is bigger than 2. Marshallian demands when M is smaller than 2. Write the consumer's general Marshallian demands. Let's see. So did I? Yeah, let me skip. Oh, I did number 20. Okay. So I wrote out carefully for 33, which is, no, that is 33. Here I'm making videos all day. So, all right. So here's what I'm going to do. I'm going to find my marginal rate of substitution. So my marginal utility of X1. Marginal utility of X1 is going to be 2/3 X1 to the minus 1/3. Reduce the power by, bring the power out front, reduce the power by 1. This is going to be a constant that'll zero out. So here's my marginal utility of good 1. Here's my marginal utility of good 2. So my MRS is going to be 2/3 X1 to the minus 1/3. Compare this to the price ratio, which is 2/3. 2/3 cancel, so my optimal selection of good 1 is 1. Remember, with quasi-linear utility, there's one of the goods that the consumer is completely fixated on. Like, they're going to make sure that they're going to get that amount. And so Bob's going to get 1 unit of good 1. What if income is smaller than 2, meaning Bob can't afford a full unit of good 1? Well, Bob's going to buy as much of good 1 as Bob can. So M divided by P1 is going to be Bob's demand for good 1. And then Bob's not going to buy any of good 2. When will Bob buy good 2? Well, when income exceeds the amount that Bob needs to get the units of good 2 that Bob's demanding, that 1 unit of good 2. So here's Bob's demand. X star is going to be equal to 1 if M is bigger than or equal to 2. Bob's going to buy his 1 unit of 1, and then he's not going to buy, and then if income is bigger, then Bob starts buying good 2. So demand for good 2 is going to be M minus 2 over 3. I'll talk about that in a second. Bob's demand for good 1, if income is smaller than 2, is just going to be, well, I'll exhaust my income on good 1 and get as much as I can. And then I won't buy any of good 2. All right, so we had our demand for good 1. It was 1. Let's find our demand for good 2. So here's our price ratio. Let's put in 1 here for X1 and solve. So it'll be M minus 2 divided by 3 is going to be my demand for good 2. Notice good 2 is only going to be demanded if income exceeds 2. All right. And then the way that I wrote up the solution, I have X1, X star is equal to the minimum of M over 2 and 1. That's because X1 never exceeds 1. Bob's never going to spend more than Bob's never going to acquire more than 1 unit of good 1. Bob is focused on getting 1 unit of good 1. So we'll get at most 1 unit of good 1, and then starts buying good 2. All right, so I skipped question 34 when I was coming in. So here's 34. Consumer with these preferences, Cobb-Douglas preferences, wants to hit a utility level of U bar. Write down the expenditure minimization problem, solve for the Hicksian demand, find the expenditure function. All right, so 34. Let's see. That's this right here. So my objective is this, because the utility was X1. That's not right. That's not right. My objective, no, I wrote this up wrong. Oh, you gotta be kidding me. So this is the constraint. This is my utility function. So this is definitely the objective. The objective function is my expenditure minimization. So my objective function, how did I not see that? I can't believe it. Well, all right. So my, so here's my objective. My objective is, well, and I've done this with x's. This is going to be px times x p. I should just do this in LaTeX, but I don't have LaTeX open. And then times y. My objective is going to be my expenditure. I don't know if I can fix that. My objective is I'm minimizing this subject to the constraint of hitting my utility level of U bar. Which is obvious when you see my partials, because you're like, where did this P1 come from? Well, it's actually Px. It came from this right here. The partial of this stuff with respect to x is going to be Px minus a lambda times this stuff here. All right. Anyway, so then the MRS is going to be Px over Py. What? The MRS, the tangency condition is going to be Px over Py is equal to y over x, right? Fortunately, our Cobb-Douglas expenditure minimization problem has the same tangency condition as our Cobb-Douglas utility maximization problem. And so this right here, this minus y over x is equal to minus px over py. That's familiar, and that is exactly the same tangency condition. So I don't know, if you have questions here, I would look at the expenditure minimization video that I've got. And that would, I'll walk through that more carefully. This is my substitution I'm going to make. Y is equal to x over px over py. And then I'm going to substitute into the constraint. Remember, with optimization, you're going to maximize or minimize, generate your first order conditions, solve the system of equations for the tangency condition, plug that into the constraint. Here, the constraint is this portion. The objective is actually this portion. So I'm going to plug my tangency condition into the constraint. This obtains my optimal values, which I'll plug back into my objective to get the value function, in this case, which is the expenditure function. That's this right here. All right, so plugging into the constraint, I've substituted for x here, so I'm going to y over px or py over px, or y is equal to the square root of px over py u bar. And then over here, I'm substituting for y, so I'm going to get x squared px over py, or x is equal to the square root of py over px u bar. And I'm going to plug those in. These are my Hicksian demands. I'm going to plug those into my objective function. That's what this is doing. And that's my expenditure function. All right, 35. Consider the following two utility functions: perfect complements, perfect substitutes. Find the demand functions, find the indirect utility function, find the expenditure functions. Comment on the respective functional forms. All right, so utility maximization for fixed proportions, for perfect complements, is going to require x is equal to y. That's just replacing the comma with an equal sign. That's the line through the corners. And then we'll plug that into the budget constraint. So I've done that. Substitute into the budget constraint. X plus x is equal to m, or xpx plus xpy is equal to m. Factoring out an x gives me x is equal to m over px over py, but it's the same for y. To get the value function, you plug these Marshallian demands into my objective function, into my utility function, put the optimals in here. So the minimum of m over px py is going to be my indirect utility. That's just m over px py. My expenditure function, we're trying to minimize my expenditure, pxx plus py, subject to the constraint that utility has to hit this level. It's definitely got to be the case that x equals y. Otherwise, there's waste, right? So following our general perfect complements functional form, we know that x is equal to m over px plus py, y is equal to px over py. So there, this is this. The expenditure necessary to hit this level is exactly the income we found from before. And then we're done. Perfect substitutes. The utility maximization requires consumers to exhaust their income on the least expensive good. So my demand is either going to be x is equal to m over px if the price of good x is smaller than py. This is the all x solution. If the price of x is, well, remember that this was, the MRS is 1. So if price of good x is less than price of good y, then my MRS is steeper than my budget constraint, so then it's all x. The opposite, if the inequality is reversed, then it would be all y. My value function, let's plug my demands into my utility function. My value function is going to be maximum of these two. The consumer is going to spend their money on whichever yields the highest utility. So I'm either going to consume m over px or m over py according to whichever is going to give me the highest utility, exhausting my budget on x or on y. The expenditure, well, I'm going to think about hitting a particular utility bundle, buying either only x or only y. So my utility is going to be, what, x plus y. And my utility is going to be either x equals m over px or y is equal to m over py. Consume whichever is larger, which is determined by the smaller the prices for the reason from before. All right, so if price of good x is less than price of good y, then my utility is m over px. The expenditure is u is my utility level, whatever's the utility level, so m over px times the price of good x, which is just m, and so on. Functional forms for my value function and the expenditure function resemble the utility function for the other case, which I think is kind of cool. So I don't know, I'll go through this carefully and see this relationship. That's a little bit of like economic theory. It goes kind of beyond the type of thing I'd ask on most exams. Most semesters. Consider the following utility function. So this is x1 to the 1/2, x2 to the 1/2. Prices are 1 and 2. Fix m and find the Marshallian demands. Show the indirect utility function is this thing. Find the Hicksian demands. Okay, so my marginal utility of good 1 is 1/2 x1 to the minus 1/2, just taking the partial. Marginal utility of good 2, similar. Take the ratios or divide and then set this equal to the price ratio. Solving, we find our tangency condition. Our optimality condition is 4x2 is equal to x1. Plug this into the budget constraint, x plus 2x2, or x1 plus 2, 1/4 x1, x1 plus 1/2 x1 is equal to m, or x1 is equal to 2/3 m. So my demand for x1 is 4/6 m. My demand for x2 is going to be m over 6, just substituting back into the budget constraint. All right, the next thing I want to do is I want to say, show the indirect utility function is this, then find my Hicksian demands, so on and so forth. So, all right, so here were my demands. I'll plug them into my, you plug them into your utility function to get your indirect utility function. So here I'm evaluating my utility, which is x1 to the 1/2 plus x2 to the 1/2 at these optimals. Good. Now what I've done is I've said, okay, I can pull out a 2 if I take the square root of 4. That lets me pull out a 2. So I'll have the square root of m over 6 plus here, this is the square root of m over 6. So I have 3 of these. I'm going to do this addition. Okay, now I want to bring this 3 back inside. How can I do that? To bring this 3 back inside, I would need to put a 9 here, right? So if I put a 9 there, then I've got the square root of, then I've got 9 over 6, or I've got 3 over 2. So square root of 3m over 2. So the missing step here is that to bring this 3 inside, I rewrite it as a 9 when it comes inside that 1/2. Okay, that's what gets us there. Hicksian demands. So there we have to solve our expenditure minimization problem. I did not write that out. So, and I'm not going to be able to do that. I'm not going to be able to do that here. So Hicksian demands, in order to get those, well, you'd minimize the expenditure P1 x1 plus P2 x2 subject to this budget constraint. And if you do that, our Hicksian demands are going to be 4/9 u squared and then 1/9 u squared. I don't think I have this. It's super frustrating. Okay, and then the rest of it was just sort of an algebraic manipulation. I don't know. I'm not super bothered by it because I mean, maybe I'll come up and I'll fix this later on. Most semesters, I would judge that as being too algebraically involved to make for a good question. My philosophy, I should make a separate video. My philosophy for exams is I want to give you questions where you're able to demonstrate that you know economics and where the algebra and the math doesn't get in the way of me being able to assess that. And so some of these problems involve what I judge to be needless algebraic manipulation. So, we did this already. And so those are not good candidates. Doesn't mean that there's not going to be hard questions on the exam. There's hard questions on the exam. Of course there are. But they're ones where they're a lot more thinking and a lot less like thinking about the specific math trick, if that makes sense. So, all right, consider the following utility function. So here's one of our perfect complements, perfect substitutes combinations. Combines elements of substitutes and complements. Consider the following two cases. Assume x1 is bigger than x2, what's the consumer's MRS? Assume x1 is less than x2, what's the consumer's MRS? This is what it looks like. You replace this comma with an equal sign and find the line through the origin that goes through the corners. It's going to be x2 is equal to x1. Above, it's going to have a slope of 3. Below, it's going to have a slope of 1/3. Then my comment is, well, if x1 is bigger than x2, then this needs to be a 3 here. Then utility is driven by this portion. Why? Because utility is driven by the smaller of the two. So if x1 is bigger than x2, if x1 is bigger than x2, this portion is bigger than this portion. So utility has to be driven by this portion because utility is whichever is the smaller of these two sides. If x1 has more in it than x2, if there's more good 1 than good 2, then the smaller of the two is going to be this side. So I'm going to be on the bottom portion. So we have an MRS of 1/3. The reverse is true if the bundle has more x2 in it. Then my utility is going to be driven by this portion. And so my MRS is going to be 3. When the prices are 1:1, price ratio is 1, consumer purchases at the Kinked, the optimal bundle, 6 is 6. And so you can, we can plug the x1 equals x2 into the budget constraint and then solve for the amount of x1 and x2. It has to be 6 of each, right, if the prices are 1. And then the similar exercise when the bundle is when the prices are 1-3. I know I fixed this. I know I fixed this before and know I fixed this problem, and I don't know what happened to that file. It's super frustrating. And so anyway, I know I fixed this anyway. But I didn't fix it for this semester. I fixed it in the past, and then I found an old file that I made of good questions, and then anyway. All right, so consider the following utility function. This one, find the demands when the prices of the goods are 3, 1, income is 40. Find the demands when the prices are 1, 2, income is 40. Find the new income now required to consume the original bundle at the new prices. Find the optimal bundle, the new prices when the consumer has income. Yeah, so okay. I'm sort of over making videos at this point, so I'm gonna kind of do my best. This is like in the middle of an ultra marathon, and you just want to be done. So, all right. So find the demands when these are the prices. Okay, well, I'm going to replace this comma with an equal sign. That'll give me the line through the origin that connects the corners. So it's going to be x2 is equal to 1/3 x1. That's this right here. Plug this into the budget constraint. 3x1 plus x2 is equal to 40. All right, 9/3 x1 plus 1/3 x1 is equal to 40. 10/3 x1 is equal to 40. And then solving, x1 is equal to 12, x2 is equal to 4. So that's part A. Now let's find the demands for these prices. That's this. So the preferences never change. It's the prices that change. All right, so I'm going to substitute this into this now. Solving, x1 plus 1/3 x1. And then 4/3 x1 is equal to 40. x1 is equal to 30. x2 is equal to 10. Good. Now I want to do part C, find the new income that I would need at these new prices. After the price decrease, what's the income necessary to achieve this bundle here? So what I'm going to do is I'm going to take the new prices, 1 times the old bundle, 12 plus 1, 4, and say, I'd need 16 at these prices to attain the bundle that I consumed in part A. Now part D, find the optimal bundle at the new prices when the consumer has income that we found. So suppose I actually have only 16 in income, how much am I going to buy? So now I'm going to take the new prices, I'm going to take x1 plus x2 is equal to 16, not 40. I've already made the substitution. x2 is equal to 1/3 x1. Solving, x1 is equal to 12, x2 is equal to 4. I feel like that's not right. What do I want to do here? Is that right? D? No, that is right. Yeah, it is right. Okay. All right. So find the values, calculate the numerical values for the substitution effect and the income effect. So the substitution effects is a change in consumption due to price that changes when purchasing power is held constant. Income effect is a change in consumption due to purchasing power that changes when price is held constant. Okay. So that's part E. By part A and part D, we know part A and part D, we know our demands. The substitution effect is just how much the consumer changes consumption in X1 in response to the change in price while holding purchasing power constant. Well, our demand for good 1 is still 12 in both cases, comparing A and D, so we know the substitution effect is 0. That's not surprising because these are perfect complements. Now find the income effect. This is the change in my demand for good 1 when only the income changes. So the change in purchasing power given the change from M to M1, holding prices constant. So this is comparing A and B. So I'm going to have 30 minus 12, 18. That's the income effect. The entire consumption response comes through the income effect. This happens. There's no substitution. These are perfect complements. This is a good demonstration problem. It's a good way to sort of understand what's happening with the income effect and substitution effect. Might be something I do in class for a review or something, but it's not like a question of this form doesn't make for a very good exam question. It's more of like learning about substitution and income effect and building intuition rather than like a good demonstrating. It's like a demonstration. It's a problem that teaches you something more so than allows you to demonstrate. And so it's not a good exam question. Consumer's utility function is given by 10xy. Currently, the prices of the goods are 3 and 5. Income is 150. Find the MRS. All right, well, with this demand, this is Cobb-Douglas demand, the MRS is going to be y over x, MUX, MUY, y over x. Compare this to 3/5. Okay, substitute that into the budget constraint. That's this. Plug into the budget constraint, yields 3x plus 3x is 150, or x is 25, y is 15, right? And then substituting for budget constraint defined for y, that's this right here. All right. Suppose the price of good X doubles, how much income is required so the consumer is able to purchase the original bundle? So suppose the price of good X doubles, now the price of good X is 6. To purchase 15 and 25, the consumer would need 6 times 25 is 150 plus 5 times 15 is 75, or $225. All right, and then the next thing, suppose after the price of good X is doubled, how much income is necessary for the consumer to reach their old level of utility? All right, so the old level of utility is going to be 10 times what 25 and 15 is going to be 3750. All right, so this is 2 equations and 2 unknowns. This is my first equation. My MRS is going to be y over x is equal to 6/5. Okay, let's substitute this into that equation. So 10x substituting for y and then solving gives me a demand for x is going to be 1767. My demand for y is going to be 21.2, but I need to know how much income this is going to cost. So this is the amount that I'm going to need after the price change to attain that same level of utility. Now I'm going to plug this into my budget constraint with those prices and find the income that I need. It's 212.2 is my income. Actually, what we'd have to actually give the consumer, they already had $150. We'd only have to give them $62.20 since they already have $150. And I'll put this here where I've written this out. And I see this is kind of freezing up a little bit, and there's a lot of nonsense happening in the house around me that I'm going to need to go take care of. And so I'm going to go outside and use my cross-country skis because it snowed today, and there's almost never a day where the snow is good for me because usually I'm driving, but I'm not driving today. I can ski. With these skis that I bought with the goal of being able to cross-country ski a whole bunch, this will be like the second time in a long time. So anyway, hope you enjoyed the video. I'll leave the comments open if you have questions, and good luck on your exams.